Welcome to The Road to Zero, a future-proof podcast, as we explore the changing nature of our economy as we look for prosperity and opportunity in not only preserving, but also improving our environment. All right, welcome to The Road to Zero. Today we have Gerard Campeau, a VP of Technical Sales of U1 Incorporated. Welcome, Gerard.
Pleasure to be here, Nick. How are you today?
Yeah. Very good. So tell me a bit more of how you got into the carbon capture world. Where did you kind of start from and how did you get there?
Sure. We developed an air purification system in the mid-90s. And it was really, the technology was really designed for all air, bad air, polluted air. It just happened to capture all elemental oxides, so SO2, NOx, CO2, CO. The gentleman who developed the technology in 1995, well, conceived it in 1995, he developed his first prototype in 2001. Based on that, we've transferred this technology to North America because where it is, they don't care about air quality. To be honest and frank, the CO2 capture is a North American, European phenomenon, maybe Japan and Australia. China, rudimentary CO2 capture, and the rest of the world, they really don't care. This is definitely something that is a Western phenomena, so Western country phenomena, and maybe the rest of the world will eventually catch up, but to date, not so much.
Okay, so really this thing was designed to actually capture all that bad stuff in the air for clean air, literally.
Yeah, particulate, up to 99.5% of any particulate, dust. It's really we call the UR is universal restorer. That's where the UR comes from. The one is because elements are singular, sulfur, carbon, nitrogen, oxygen, everything in the air is made up of one element combined with another to produce a molecule. And what this technology does is it breaks down those molecules into individual components, and then releases the good portions, which can be collected afterwards, and then captures the other components, the carbon, the sulfur. The nitrogen is released because it is a gas in pure form, and oxygen is released because, again, it is a gas in pure form. But carbon in its elemental form is a solid, and so is sulfur. So those two are captured in our process, and they are further processed.
Okay, so literally this thing takes this all in, separates the oxygen from their other components, lets the oxygen go, and you end up with all this solid stuff. And how effective is it at doing it? How much like carbon does it actually grab out of the air?
Our tests indicate that it's about 92% effective. So the best in class of any technology that presently is in the market, and that's all oxides. So the biggest difference we do is we don't have to have several different technologies. So with sulfur dioxide, typically they use FG. It's called FGD, and that's fuel gas desulfication technology. It uses typically a limestone. It crushes that limestone and it creates a slurry with water. They percolate through a reactor. The gas comes up, and as that percolation or shower comes down, it absorbs the sulfur and some nitrogen. And then they take it and it produces gypsum, which they sell. Now, typically that process is very expensive to operate, and they never recover what it costs them to capture that SO2. Now, from there they have to take the CO2 and they have to do something with it because it only captures SO2. So all these what I consider sorbents or absorbents, they only capture one gas, typically one or two gases, but never the trio, never NOx, SO2, and CO2. Ours does not differentiate. It captures any gas. Not only that, any VOCs, volatile organic compounds, are also separated. Dioxins, furans. So if you're burning garbage with plastic in it, captures everything. So this is how radical this technology is. We believe fundamentally it will usher in a new carbon age, primarily because of its cost structure. So we don't use any liquids in our process except water. And then we use electricity. But we don't, it's not a plasma-based technology. And plasma is an expensive uses a lot of energy to create the plasma. We don't create plasma in our technology.
Okay. And what I hear is a bit different. Not only are just taking the carbon out, and I take it you end up with some kind of solid form of carbon, you're also getting all these other elements that you can do something with.
That's correct. So realistically, we capture pure sulfur, yellow sulfur that you see made for gunpowder and additives for rubber, for any industrial process, high value sulfur, if there's sulfur in the flue stream. So the sulfur is captured. It is of elemental form. So that can be sold in a secondary market, industrially sold. The carbon is captured as a fullerene. So fullerenes are called, are allotropes of carbon. So carbon comes in many forms, many different atoms of carbon. And they're different forms. They're called Buckminster carbons. Again, it's a very kind of backdoor technology component that really not a lot of people know about. That fullerenes are very high value items. So what fullerenes are really cages. And these cages are in the shape of a soccer ball, a rugby ball, a football. They come in graphene. Everybody's heard of graphene, I think, in technical terms. Graphites. These are all fullerenes. And we produce all of these as a byproduct to these carbons.
Yeah, and for those that don't know, that's really, you can make carbon fibers with it, and graphene's got a whole bunch of new applications they're looking at. It's kind of like the wonder material that they're exploring next.
It is. And so what our focus is not only on the equipment itself, but the ability of that equipment to go into an emission power plant, an emitting carbon power plant, and literally clean up the entire emission coming out of the smokestack. We've had tests where our air going in is dirtier than our air going out. So our carbon count right now on Earth is 409 parts per million. We get down to about 150 to 200 parts per million on our output.
And that's a great question too, because what I hear, this is great when you have really concentrated carbon. I imagine that's the best to do when you have a concentrated flow of it running through the machine. But for like a direct, because I know there's a lot of these farms showing up where they're just drawing atmosphere air. Can this be used for that as well, or is it more just to combine with a?
It can. So there are two variants of the technology that we're testing right now. One variant we use for COVID-19, for bacteria, molds, fungus, radon. We are actually testing, very first company ever to request from a BSL-2 lab in the US, a biological lab, to test the ability for our technology to remove radioactive radon from basement air. We're also testing carbon monoxide, because those are two pollutants that people have in their houses, especially in southern Manitoba. They have, it's a huge issue. Radon is the second leading cause of cancer in the world, behind cigarette smoke. So it's a major issue in a lot of jurisdictions, and people are building to radon standards now in high radon areas by basically creating an envelope, if you will, on the basement floor, an impervious plastic. But then they're also putting in piping in the concrete with a venting system. So we're testing to all those form factors and COVID-19 is actually, we're going to be testing that as well. Our ability to literally zap, almost like a bug zapper you'd see on a house we can zap COVID-19 and kill it. And we've got documentation of that, but nothing from Western, field studies and obviously medical studies here, like stage 1, stage 2 studies that are required to make those claims. So we are going through that process now. The third variant is this goes into greenhouses. It kills anything from fungus to molds. So what it does is it allows the plants to grow at 30% higher rates of growth. Now, people say to us, well, how can that be if it takes out CO2 of the air? Well, what people don't realize is you're force feeding these plants CO2. That's not necessarily healthy for the plant. Yes, does it yield more fruit? And do they grow faster? Yes, but it puts the plants under stress. So what is that doing to our food basket? Is that creating food that is not as nourishing as food that is naturally grown? So that's our argument to that factor. So we're testing this with the University of Guelph. They're going to be testing in a greenhouse, our unit. We're also testing with several people in the U.S. Medical labs, third-party medical labs that will test to certain standards, basically that they have, guided by the FDA and Health Canada in Canada and the FDA in the U.S.
Okay. Now, I hear like this has a lot, like really, you got a certain market, and it sounds like the carbon capture conversation is kind of like taking you by surprise a little bit, because that's not originally what you were set out to do. And I hear, especially this interest now in carbon capture, your device seems to be fairly effective at it. And can you tell us a little bit about how it compares to other technologies? I know you definitely hear the cost per removal of a ton. So I don't know if you have any figures or idea of what that looks like for your system.
We do. We're at the very low end of cost per ton at $5 a ton. Now,
Really?
if you factor in the fullerenes, then we're in a negative cost.
Okay, so that's before you even sell and reuse the carbon, just to operate the device.
Just to operate the device on an electrical basis. I'll give you an idea. Petronova is a project that Department of Energy put $200 million into. It was a coal plant, coal power station in Texas. It was commissioned in 2016. It was retired in May of 2020. It was a CCS plant, basically a beta test prototype. The third one, SAS Power has one in Alabama. Same contractors built that plant. They spent $1 billion building that plant. It captured approximately, it was a 240 megawatt plant, rated nominally at 300 megawatts. They require 45 megawatts of electricity and 55 megawatts of thermal energy to run that plant. So fully 1/3 of the plant was dedicated to carbon capture of its production of electricity. So because it was so radical, they had to build a secondary natural gas generating plant next to the coal plant just to run their carbon capture. Now, this involved an absorbent technology, which is liquid, chemical, which would basically saturate, absorb the CO2. That CO2 is then embedded in a liquid. That liquid is then heated. When it heats, it liberates the CO2. That CO2 is then collected. It's compressed, sent via a pipeline down to a sequestering, an old mature oil field where it's dumped into the ground at high pressure, and it's saturated into the rock. And hopefully over time, that rock will absorb that CO2 and capture it. But the jury's out on how effective that is and how much that rock can actually capture over time. Now, that absorbent then, because it's heated, has to be then cooled again through a cryogenic process. And then it's reintroduced into the process. That absorbent needs to be replaced. It oxidizes, it gets old, it has to be replaced. So there's ongoing costs. So now you're talking about all these processes: heat exchange, compression, pipelines to 80 miles. This pipeline's 80 miles away. The field is 80 miles away. So they had to sequester all the land. They had to have eminent domain, just like any pipeline would have to have. They had, town councils fighting against them for this. So this is the standard right now that most CCS is under. Now, if you're a Suncor or something like that, you can utilize your carbon in your process right on site, but you still have that enormous energy that you require for all that liquid to be moved around.
Yeah, and then tell us a bit about how your process is different. So no, you don't use any of that, no liquids. So
We
you're
do
using
use water,
electricity.
recycled water we do use. So
Okay.
how our process works is we basically have a reactive plate and a waterfall, and they're literally parallel to each other. So as the gas passes uninhibited between them, that reactive plate creates a very high reactive zone. That reactive zone literally blows apart the molecules of oxides. And when those oxides are blown apart, those elements are liberated and they're picked up by the anode, which is the water. So they're absorbed, the carbon goes into the water, the particulate goes into the water, all oxides, everything you can imagine that comes from that combustion is absorbed. Even the water is consumed in the process. Even the H is consumed. So the hydrogen of the H2O, which in combustion could be anywhere from 75 to 80%. So those stacks you see, that's vapor, water vapor. That's not CO2. You don't see CO2. You can't see it. So the industry demonstrates a smokestack and says that's the CO2, but that's not. That's 85% is water vapor. That's part of the combustion process. You need water is released, just like in your muffler when you're driving and you see water come out of a tailpipe. That's the water in the fuel that's being burned.
Yeah, vapors
so
coming
this
out.
is no different. So we capture the H of that H2O. The O2 is released into the atmosphere. So we're literally force feeding fresh oxygen into the atmosphere with our technology and nitrogen.
And that's interesting. What happens with the hydrogen?
The hydrogen acts as a coolant, a cryogenic coolant in our technology. So what we do is we create an atmosphere of high temperature and low temperature. And it's sort of like burning yourself and taking an ice cube and putting it on that burn to cool it down. That's what our process does. Because it does that, it acts almost like methane reforming. So methane reforming is a very blunt force of taking methane, CH4, and just bombarding it, just like a hammer with steam at very high temperature. And from that methane reforming, the chemical bond of the C and the H4 are separated. The H is collected, and what's left is CO, carbon monoxide. When that is ejected into the atmosphere, it bonds with another O and it creates CO2. So we can actually take our technology and attach it to a large industrial user of CH4, and we can physically capture that CO2 from those emissions. But I even go a step further. We believe that we can take our technology and we can actually replace that massive amount of energy to create CH4 into hydrogen and carbon, and we can eliminate that completely. And we can use, as opposed to using a large knife, we use a scalpel approach. And because we use a scalpel approach, the amount of energy we require is a fraction of what they require today in the process. So we're talking about a fundamental drop in efficiency by up to 1/4 the amount of energy. So back to that plant now is consuming roughly 100 megawatts to treat that 300 megawatt nominal coal-fired plant. We only need 9 megawatts of electrical energy.
And then seeing your plants that you have both in Canada and the US, who are your customer? What projects are you currently building on?
We're actively presently talking to the oil and gas industry. Flaring, we have one customer now telling us they want to order at least 100 small units, and these small units would process up to 1 million cubic feet of gas or emissions per day. So that's a standard flaring tower, would be under that. Sometimes in the Permian, they may go to 1 million to 3 million. When they're brand new, they obviously have a lot more gas to process for flaring. But as they settle out, they drop down. So we would add 2 or 3 of these systems and then retract these systems as the flow rates decline. We have a couple of cement companies we're talking to. I would say cement, not concrete. Concrete are afterwards. Those are the guys that mix it all together. The cement guys are making the limestone and baking that, and they're the carbon intensive guys out there. The concrete guys, they are still carbon intensive, but not as much. We're talking to an LNG company that's building an LNG project. They are selling to Europe, and they have a request from their customers in Europe to be as carbon neutral as possible. So we also have some natural gas plants being built and some existing legacy plants in Alberta that people need to find solutions for. So these are all projects we're working with. We're also talking to northern communities on their diesel gen sets, which are emitting huge amounts of particulate and diesel emissions. We can clean up all those up to, as again, nothing's 100%, but we're in the mid to high 90s, and we can actually get close to 100%. But there's an added cost. Every time you go for that incremental increase in purity, you add a lot of cost to that. So, that's a judgment call based on what the customer wants to achieve and where they want to go with the technology. So that's basically where we're at right now. We're also talking to some large power companies that are looking at legacy technologies like coal that they have to find solutions for, or they have to shut down. And in a lot of these jurisdictions, they have coal that's just right there, and they have a plant right next to the coal mine, and they don't want to shut down. And the only reason they have to shut down is because the regulations are making them uneconomic. It's so expensive to put in emission capturing technology. It makes them uneconomic. It's not that they can't compete. It's just that they have so much more costs, capital costs, and operating costs to meet certain air standards. That's what makes them uncompetitive.
It sounds like business is amazing. And what do you see as in the future for your company?
Well, I see us partnering right now with a few majors as our core. That would get us immediate projects and recognition to raise money. Obviously, everything works on money, and to scale these into a large application. Right now, we're quoting a very large application in the U.S., a coal-fired plant. Believe it or not, people still want to build coal-fired plants. It's a foundation of power here, baseload power in North America. Now, our technology is a bridge, and and that's how I sell it. It's a bridge from the fossil fuel to the new age of green. And I sell all technologies. I don't care if it's green, if it's solar, if it's wind, if it's biomass, if it's nuclear, hydro. It doesn't matter to me. They all have a place on this planet. And if we want to keep our standards of living, we have to continue using fossil fuel for the foreseeable future. I just want to give the fossil fuel industry a chance to survive and prosper along with everybody else, and let them compete on a one-to-one basis. That's what I offer, is an ability for everybody to compete on a level playing field with no governments picking and choosing winners and losers, because we know what happens when government picks winners and losers. It doesn't work. We need private enterprise to pick winners and losers, and we need technology. Technology will solve anything. It's just a matter of the will of everybody to come up with better technology.
Yeah, and I definitely hear your technology really resolves a big issue around carbon that's really been plaguing the industry and really is a big concern at the moment. So it's quite a a fundamental change in the landscape.
Yeah. We can dwell on the CO2 or the carbon capture, but fundamentally, when I'm proposing with our technology, what we're proposing with our technology is a fundamental shift of using carbon in a solid form for thousands of applications that don't exist today. If you look at fullerenes today, at C60 fullerene, refined C60 fullerene is $100 US a gram. C80 is $300 a gram. Endohedrals with a nitrogen atom inside the cage is 100 million pounds a gram. There are atomic clocks that are used on MEMS devices for guidance system. This is what we're talking about. We need carbon because we need to be able to take, if we're going to drive autonomous cars and flying vehicles, we need accurate GPS. And the only way we can have accurate GPS is be able to have an atomic clock that has no time differential from the time it transmits from a satellite down to Earth to the time it makes a decision on whether there's another vehicle going to hit it. This is extremely accurate technology. Atomic clocks allow that to happen. And we need endohedrals to do that. So carbon has an extremely versatile platform to work from, not only in pharmaceutical delivery of drugs to the body, but everything from batteries to windmills to you name it. It's in everything. Graphenes, graphites. Carbon is everywhere. People just don't realize how versatile carbon is and how many products, even the toner in your printing machine uses carbon. Now it uses a lower form of carbon, but it still uses carbon.
Yeah, and the beauty, you've got a really effective way to actually bring that carbon, instead of being a source of pollution, to actually being a valuable commodity.
Exactly. I mean, carbons are used for fertilizers to grow plants. The only problem with carbon is when it's in the air, it creates greenhouse GHGs. But when it's sequestered in the ground, it's a fertilizer for plants to grow and thrive. So, this lobby against carbon and giving it a dirty name it's not correct. Carbon is positive for everybody. Our bodies are made with carbon. It's an essential part of life. It's the fourth most abundant element in the universe, carbon.
Yeah.
Everywhere.
Yeah. Yeah, we just need to get it out of the air and then we're good.
That's right. That's all we need to do, and find effective ways of doing it. And we have an effective technology that does it at the lowest energy level that I've seen in the marketplace. And I will challenge anybody to prove me wrong that our technology isn't the lowest energy required carbon. And we've already proved that we can do air-to-air capture. Our small little units, which we have already here, have already been tested, and we've dried the water out. We've actually boiled off the water and looked at what the residual is, and we have carbon in that water. So you put this in your house, you're not only purifying your house, you're taking carbon out of the air. So you're doing a dual purpose of cleaning the air in your house.
All right, well, thank you for sharing this with us. And it's very, I look forward to seeing more of this technology and see how your company develops in the future.
Thank you very much. Appreciate the time.
To hear more about our podcasts, showcase events, or the Futureproof Network, please visit us at www.futureproof-network.com.